Sudoku is a solitaire game played on a 9x9 grid, where the 81 cells are further grouped into 9 3x3 boxes. The goal is to fill each space of the grid with one number between 1 and 9, while adhering to certain rules or constraints, which are as follows. Every row, column, and box must contain all numbers 1 through 9, and no number may ever appear twice within the same row, column, or box. When observing a blank Sudoku puzzle, every square on the grid has the potential to be any of the 9 possible numbers. We could also say that they are in a superposition, occupying all 9 possible states at once. But usually a Sudoku puzzle doesn't start off blank. Instead, there are already a few numbers filled in, their superpositions collapsed to a single possibility. These collapsed cells will of course affect the possibility space of surrounding cells. We know, for example, that since there's a 5 in this row, that none of the other cells in the same row, column, or box may contain a 5, so we can propagate that knowledge to those affected cells, removing 5 from their superpositions. After propagating all of the constraints imposed by our initial conditions, the next logical thing to do is to look for the cell with the lowest number of remaining possible states. Or to put it another way, we want to find the cell with the lowest entropy, and collapse it to a single possibility, once again propagating the results to affected cells. The reason we prioritize low entropy cells is that there are fewer states left to choose from, and so it's less likely that we'll make a bad choice. We'll continue this process of iterating over the puzzle, collapsing and propagating, until all of the cells are collapsed to a single possibility, and the puzzle is solved. Now, you were probably expecting an explanation of how the wave function collapse algorithm works, and not one of how to play Sudoku, so let me explain. The wave function collapse algorithm is a procedural solver that takes a grid of cells, each occupying a superposition containing all possible states for that cell. We call this the wave function. Each potential state for a cell, let's call it a tile, comes with its own set of adjacency rules. For example, tile A will only allow these tiles north of it, these to the east, these to the south of it, and these ones to the west. In the same way a human approaches a Sudoku puzzle, the wave function collapse algorithm will look for the cell with the lowest entropy, or pick one at random if entropy is equal among all cells, and collapse it to a single tile. It will then go through the process of propagating the consequences of this collapse to other cells. For example, if tile A was selected, we know that the superposition of the cell immediately to the east of the collapsed cell must now be restricted to only contain the valid neighbors of tile A in that direction. And since this cell has now had its possibility space shrunk, the wave function collapse algorithm will need to continue propagating these new consequences to cells neighboring that cell, and so on, until all tiles invalidated by the collapse of our initial cell have been removed. This is a single iteration of the wave function collapse algorithm, and it will continue iterating over the wave function, starting again by finding a low entropy cell and collapsing it, until all cells contain only a single tile, be it through the invalidation of all other possible tiles, or through collapsing that cell to a single possibility. Once this occurs, we can say that the wave function has collapsed. As you can see, the wave function collapse algorithm is actually pretty straightforward, and because it bears more than a passing resemblance to the process of solving a Sudoku puzzle, it's even more straightforward to explain and intuit. Now that you have a good idea of how the wave function collapse algorithm works, we need to talk about those adjacency constraints I mentioned earlier, as this is the thing that you'll find varies the most between different wave function collapse implementations. Here are the modules I'll be using for my wave function collapse implementation. They're all built to a 1-unit cube grid, ready to be slotted together. Next, we need to find a way to tell the wave function collapse algorithm which modules can slot together and which ones can't, and in which directions. It needs to know that this is valid, but this isn't. There are a few ways to achieve this. The original wave function collapse implementation has a novel approach and includes an additional step before running the solver that analyzes an example of what the output should look like. It can then break the example down into tiles and check which tiles are placed next to one another, and will consider those combinations valid. I've actually already done another wave function collapse implementation that does exactly this, using a tile map as the input. Before running the solver on a blank tile map, the algorithm looks at the example tile map and takes note of which tiles are present, and any tiles that are adjacent to one another in the example are considered valid neighbors when solving the wave function. You can have a play around with this on itch. The link is in the description. Another way to decide which neighbors are valid and which ones are not is to use a socket system, marking up each tile edge with some kind of identifier and invalidating adjacency for any tiles whose sockets don't match at the cell boundary. Something similar can be seen in this now famous wave function collapse demo by Oscar Stahlberg, also linked in the description. Here, each tile's socket is dictated by the color of a pixel at 3 fixed points along each edge of the tile, and adjacencies are validated based on whether or not the adjacent tile's colors match at these 3 points. For this demo implementation, I'm going to be using a system heavily inspired by this also pretty famous Infinite World wave function collapse demo by Marian42, and here's how it's going to work. In order to validate adjacency between modules, each module is going to need to contain 6 lists of valid neighbors, one for each boundary face. Whenever we collapse a cell, we can then remove any modules from neighboring cells which aren't present in our list of valid neighbors, just like in the first wave function collapse example from the beginning of this video. To create these lists, we'll need to label each module with sockets, one for each face, then check the validity of modules being adjacent to one another by checking their sockets and consulting some simple rules about which sockets may or may not fit together. The first thing we'll do is loop over every module in our set and store the positions of each vertex that sits along each edge of the 6 boundaries. We'll store and label these boundary profiles as we go, assembling a dictionary of socket names and their corresponding profiles. There's also some special markup we need to do for symmetrical and asymmetrical sockets. We'll tag symmetrical ones with an S in the socket name, because we know that regardless of orientation, a symmetrical socket will always fit with itself, whereas asymmetrical sockets will only ever be valid when placed next to a mirrored version of themselves. We do this by mirroring the vertex positions of each socket and checking if they're still identical. If they are, then we label the socket as symmetrical, and if they're not, we store the flipped and unflipped versions as 2 different sockets and mark one of them with an F. For the top and bottom boundaries, we have to do something special as well, storing 4 versions of each socket, labeling them with a rotation index 0, 1, 2, or 3. Vertical sockets will then be considered valid neighbors if they have the same socket name and rotation index. As we analyze more modules, we'll find that we've already come across some of these sockets, and instead of storing new entries, we can instead just apply the matching socket name and move on. Eventually, we'll have marked up every single module in our set with sockets, and now it's time to start building those lists of valid neighbors, using all of this information we have. Before moving on to creating the actual neighbor lists, we'll need to talk about the concept of prototypes, which is borrowed directly from Marian42's implementation. Prototypes are the metadata for our modules, containing information about which mesh to use, what the rotation of that mesh should be, and the 6 lists of valid neighbors. This allows us to get around needing to export 4 different meshes for each module to cover all possible rotations. Instead, we just create 4 prototypes that reference the same mesh, but with a different rotation index for each. We'll be writing our list of prototypes to a JSON file, which we can load in our game engine as a dictionary. So let's start building prototypes. For each of our modules, we'll create 4 prototype entries, one for each rotation. At this stage, the prototype will contain only the mesh name, rotation index, and list of sockets, which we'll swizzle around depending on the rotation index. Now we have a list of every possible orientation of every module. Next, we'll need to compare each prototype with every other prototype 6 times, once for each direction. We'll check that the opposing sockets are valid using our adjacency rules, and if they are, add the other prototype as a valid neighbor to the relevant neighbor list for this prototype. This might seem like a lot of repetition, but to create the prototype list for this admittedly small set of modules, it only takes about a second. One final thing to note is that a module might not contain vertices along every boundary face, so when this happens, we store the socket name as being -1, and after creating all of the prototypes, a blank prototype is added to the list with -1 sockets along all faces, and no mesh reference. This allows our wave function solver to place blank space in the same way that it places meshes, and so simplifies the whole process a little bit. And that's it, we're done. We've got all the data we need to start implementing our wave function collapse solver. Here's what the prototype data looks like, and here are all the meshes they reference, ready to be loaded into the engine. I won't be going over the code that does all of these steps line by line, simply because it's 400 lines and a bit messy, and so doesn't make for good entertainment. If you understood everything up until this point, and you know how to do a bit of programming in your DCC of choice, this should give you a really good head start. If you'd like to get your hands on my code, you can find it over on my Patreon page, linked in the description. Next up, we'll need to write our wave function collapse solver in Godot. Again, the code for this is quite long, so I'm just going to cover the most essential parts. First off, we need to load our prototype data, and this is the function that does it. As you can see, I'm simply opening the JSON as a text file from the root directory of my Godot project, then parsing the text result to return a dictionary. Next, we initialize our wave function, which is as simple as creating a three-dimensional array, filling each cell with a copy of our prototype data. Then, to get everything started, we create a while loop that breaks if our wave function is fully collapsed. This function simply checks if any of the cells in the wave function still contain more than one entry. If it hasn't fully collapsed yet, we tell the wave function to iterate. The iterate function should sound familiar from the beginning of the video. First, we find the cell with the lowest entropy, which we do by looping over the cells to find the one that contains the lowest number of possible prototypes, with some randomization in case there's a tie. Then we collapse the chosen cell by picking a prototype at random from its list of remaining prototypes and remove the rest. Finally, we propagate those changes to the rest of the wave function. So far, so Sudoku. But before we wrap up, let's take a look at how the propagation actually works, as this is the beating heart of the wave function collapse algorithm. To start with, we add the coordinates we just collapsed to a stack, which is just an empty list at this point. Then we head into a while loop that will continue looping as long as there is still a cell in the stack. At this point, we know that there's exactly one cell in the stack, and so we pop the last entry from the stack, leaving the stack empty. Next, for each of the 6 directions, we get the coordinates of the next cell in that direction, along with a list of prototypes currently contained in that cell. Then we can just check what the list of valid neighbors for our current cell is, and compare the two lists. Any prototype in the neighboring cell that's not considered valid is simply removed from that cell's superposition, which is what the constrain function here does. Finally, if a cell's superposition was modified by this propagation, we add its coordinates to the stack, so that it can propagate the consequences of constraining the possibility space to its neighboring cells. This will continue looping in this way, constraining cells, adding them to the stack for further propagation, and so on until the stack is empty. Then, iterate will be called again, and there'll be another round of propagation, and again until every cell in the wave function contains only a single prototype. Then it's a simple case of rendering the result, which is done by looping over the wave function one more time and instancing the corresponding mesh at the correct position and orientation for each remaining prototype. And that's it, our wave function collapse implementation is complete. As you've seen, the solving algorithm is actually pretty straightforward, and most of the complexity in this example actually came from creating our adjacency constraints. Something I haven't covered in this video is weights, as a way of telling the algorithm to prefer picking certain modules over others. But hopefully after watching this far, you already have a good idea of how this might fit into your wave function collapse implementation. As always, if you enjoyed this video and would like to see more content like this, be sure to like and subscribe, and maybe check out the other videos on my channel. If you'd like to get your hands on the project files for this video, head on over to my Patreon page, linked in the description. And if you really like this video, please consider supporting me on my mission to create great quality, densely packed educational content that respects your time. Thank you very much for watching.